Okay, just before we start with revision problems, do you have any specific questions that you want me to go over? Okay. I will start first with the problems on renewable energy, solar energy or wind energy or hydropower. All I want you to know is how to apply the basic knowledge we have tackled in chapter 2 and 3 if you want to renewable energy. So we already have considered in previous chapters how to deal with let's say convection heat, heat in form of radiation, transient heat, and now we'll apply them to test, for example, renewable strategies, how they perform, how to calculate their efficiencies. To start with, I will talk a little bit, I'll give an example, let's say about a solar energy problem and how we can use energy balances in a solar energy problem in order to know if the solar system is able to handle the application we have or not. Okay, so you can have a variety of possible problems. You know, for example, solar energy, you can use this energy to do what? What are possible applications? Who can give me an example? The heat extracted from solar energy, how you can use it?
Air conditioning, producing electricity.
Okay, we can use it for air conditioning. We can use it to produce electricity. We can use it to heat water. Okay, so if we have a problem and we want to see if the solar energy is enough or not, what should we do? We should do an energy analysis, okay, to know. And the easiest example will be the following. Let's say I want to, you know that we can use a lot, solar energy can be used for underfloor heating, okay? Let's say you have a solar panel, a solar system, and you want to select, let's say, a minimum number of panels. What is the minimum number of panels needed to ensure underfloor heating? Okay, so let us say, for example, we know what is the area of each panel. Okay, so a panel is characterized by a certain area A. We know the heat flux coming from the sun. So let us call it S. Okay, it will be in, let's say it's, for example, it's equal to 400 watt per meter square. So we can say that the solar flux hitting the solar collector is equal to 400 watt per meter square. We have the area per channel is given. Okay, let's say, for example, the area per channel is 1.5 meters square. Okay, and we can say, if I tell you, for example, that the maximum flow rate of water through one panel, maximum flow rate of water through one panel is 0.1 kilogram per second. Okay. Now, design a convenient solar system in order to heat uh, 100 liters per second of water from 25 to 60 degrees. Okay, so this is an example. We need to find what is the number of panels needed in order to perform the floor heating application. Okay, so first, whenever we give this, we should also give us the efficiency of the panels. Okay, knowing that, so we give also the efficiency of a panel is equal, let's say, to 85%. And the absorption coefficient of the panel alpha is 90%. So all we have here to do is to write the energy balance for the system. We are absorbing heat, and this heat is used to convert it as sensible heat for water to increase its temperature. So neglecting losses, of course. Yes. So in case they didn't mention losses, you will consider that the system is well insulated and will not have loss. Of course, in real case scenarios, we have losses. You know how we can take this into consideration, and we can always have a safety factor. So let's say we obtained that we should have a certain 7 panels, for example. We can say, to be on the safe side and account for possible losses, let's say let us use 8. Okay, but in the problem, if they don't specify for you any safety factor, or they don't say what is the value of losses, you can work without losses. In general, engineers at the end, when they do a design, will take a certain safety factor into account in order to consider all things that were neglected in the analysis. All we can say here is that heat that is absorbed okay, if you want, what should I do? Q absorb times what? I'm absorbing energy from the sun, but I should not forget that I have a certain efficiency of my system. So the efficiency sometimes can include some possible losses and a possible deficiency of the mechanical system used. So I should multiply the absorbed energy by the efficiency, because this heat will not be totally transferred to water, equals to here, since we have to search for the number of panels, so we should write times n, because we don't know what is the number of panels to use. Okay, now Q absorbed for each panel, so Q absorbed per panel is equal to alpha times G times the area of each panel, area of P. So we have alpha, we have G, we have area of the panel, we have the efficiency of the system. We are just looking for the number of panels to use, equals to the other side. Okay, so from the other side, we have that m dot Cp delta T. So this is equal to m dot times Cp. Here, this sentence here, we don't need this. You know why? Because already they gave us enough information. I will tell you in another scenario how you can use this. Okay, so sometimes for one panel you can play with the flow rate depending on the temperature that you need to have at the outlet. We'll talk about this after, but now we don't need this information. And sometimes Sometimes they can give you extra information. So please pay attention. You don't need always to use everything given. You should select what do you need from the problem. Okay. So here, this is equal to m dot okay. Here, if they say that in total, we want to heat 100 liters per second of water. But of course, this 100 liters per second will not go through, if you want, they will be distributed for all panels, okay? But in total, since here we considered the total heat, okay? So just we can put directly m dot total of water. If you did the analysis per panel, instead if you put from this side Q absorbed times epsilon times alpha per panel, okay, then you put m dot total over n. So the idea is that because we already considered heat absorbed from all panels, we can write m dot Cp delta T, and then we can consider that in this case. But in this case, what will happen? Water, if you want, will circulate. And here we have several possibilities. Water can circulate from one panel to the other. So it will first move within first panel, then the exit from the first will move through the second panel, etc. Another strategy will be to, if you want, have parallel passes. I divide from the beginning, I divide m dot into several parts. So I have a first part that will go through the first collector, another one through the second, a third one through the third, etc. This might be more efficient because if you have the same path going through several panels, this may induce more losses in your system. Okay, so if you want, these issues of how to do it will depend on the practicality of the design. When you perform any design, you have some engineering preliminary calculations that you are doing now. But if you want after to decide, for example, if you want to do it, if you will pass the whole rate at once, or you want to divide it into parts, you should study then the head losses, etc. This will be much more complex. But here for this study now, we just need to know what is the number of panels to use, because we need to determine what is the total energy that we should absorb. Now, how to take it, if we take it as we said in series, or if we take it in parallel, it's another study. Okay, so it's m dot total times Cp times delta T. We have the mass flow rate, the total mass flow rate that we want to heat. We have Cp, we have delta T. Okay, then the only unknown is the number of panels to use. Now, let us say we found out the number of panels. Sometimes we have some restrictions. For example, this sentence, okay, can help us to know if it's possible to have a series connection or parallel. For example, if they tell you for one panel, the maximum, here I will change the numbers to see how it will fit. So here, if I tell you that the maximum number per panel, for example, is, let's say, 0.01 or 0.1, let us keep it as it is. If you have the maximum flow rate 0.1 kilogram per second, you have calculated the number, you have calculated already the number of panels, and you know what is the total number of liters per second. Okay, 100 liters per second will correspond to 0.1 meter cube per second. Okay, and since we know that for water, the density rho of water is 1000 kilogram per meter cube. So this will correspond to if we do the calculation to find in kilogram per second, it's equal to 10 kilogram per second. Okay, so in total, you have a total mass flow rate to circulate of 10 kilogram per second. And once you calculate n, you can determine then if we want to use parallel or series application. If the limit, and you should check for the limit here. Okay, for example, if they tell you that the maximum flow rate per panel is smaller than 10, then of course you should divide. You should divide into several passes. While if the maximum flow rate is above 10 kilogram per second, then the series mode is applicable. Okay, so you can have such problems with a small design question. Okay, another important thing, you should be familiar with the type of energy transfer. Okay, it is involved in chapter 2 and 3. I will not give you, of course, in the exam something very deep in convection, conduction, as we did in the midterm. But just I want you to know what are the mode of heat exchange. The convection, the radiation, what are the formulas of convection, radiation. So for example here, if I tell you, in addition to this given, if I tell you that we have possibility of losses from the panels to the external environment by convection. Okay, so I should give you then what is the convective coefficient. I give you the convective coefficient, and let me select another color here. Okay, so I tell you have losses with the environment. I give you H, and I give you, let's say, the surface TS of the temperature of the surface of the panel, and I give you T infinity. And I give you T infinity. Then you can find what is the convection, the heat lost by convection to the environment. So you can say that a Q convection is equal to, but it's lost now. And in addition, when you want to write your equation here, you should put N times Q absorbed times efficiency minus. Concerning just, I want to ask you one question. If I give you the efficiency here, you should multiply it before or after doing the subtraction? In general, when I give the efficiency of a system, okay, it is the so once I take a certain energy, what is the amount I will give it to water? So this should be multiplied by the net, the net transmitted, if you want, the net that is taken by your system. So you should do N times the Q absorbed, okay, minus H A delta T. So this is in total the energy that is, if you want, entering the solar system. Then I multiply this by the efficiency of the solar system to find what is the energy that will be taken by water. Okay, so the modification I will do here is to subtract from the energy absorbed the energy lost by convection. And if I have radiation process, okay, also I should subtract the flux lost by radiation. Any question on this?
Doctor, when we subtract,
Yes.
كيف السؤال بيجي بس أنت بنشيله.
Okay.
ما كتير فهمت السؤال كيف بينطرح.
Okay. السؤال بيكون هيك. In this case, the question will be إنه a solar panel okay, is will be hit by a flux of 400 watt per meter square. It is characterized by a certain absorptivity alpha given, okay, but also we have heat loss from the surface of the panel with external environment. So let's say I gave you T infinity, which is atmospheric temperature, the ambient temperature, T infinity equals to, let's say, 25 degrees. But when heat will be absorbed by the solar system, this will affect its surface temperature. You have a high surface temperature. Let us say we are working in steady state mode, and I give you that the surface temperature is 70 degrees, and we have losses of heat from the surface of the panel to the outer environment with a certain convective coefficient that is given. And let's say we have forced convection. If you have high wind going through over the solar panel system, this will lead to a high loss by convection. So when you want to write the total energy that is, if you want transmitted through the solar system, you should say I have plus E dot absorbed, because the absorbed energy will be gained by the system. But I will also, before it's transmitted to water, one part will be lost by the system by convection. So minus, or you can write plus E dot convection, but E dot convection is negative because it's lost by the system. So E absorbed is plus alpha times area times G. Okay, while E dot convection is minus, because I'm losing this energy, minus H times A times T surface minus T infinity equals to, this energy is transferred to water, so it equals to energy gained by water, E dot water. Okay, so the net, but of course, because we have the efficiency, so you have a heat exchanger within the solar system to transfer this energy to water. Since heat exchangers are not perfect, we'll always have losses. So we'll multiply this by the efficiency, if you want, of the solar system, which is affected by the heat exchanger type used. So then you will find what is the energy balance. And in this energy balance, the only unknown will be the number of panels. So we should not forget to multiply by N, which is the number of panels. Okay. Any question on this? Okay. Another problem, I will do a problem on chapter 8. Concerning the other chapters, okay, wind energy and hydropower, also you are just responsible of knowing how energy is converted from one state to the other. Okay, and for example, in hydropower, what is the main equation used? The whole hydropower system is based on the concept of exchange of energy. So let's say if I construct dams, okay, with a certain height of water, when I open the gate, or when I have discharge, I will convert this gravitational energy into kinetic. So the whole concept of dams and hydropower will lie on conservation of mechanical energy, or the Bernoulli equation. Of course, in reality, we have losses, it's true, but as a first design, using conservation of mechanical energy will help us into design of dams. Okay, and for the case of wind energy, I just want you to understand how we got the Belt's limit. So you should understand the physics behind it and how we write the equations to reach this limit. Okay. Now we'll do together another problem on chapter 8, which is on economical analysis. Please, for chapter 8, whenever you write the equation, you should develop it as we learned together in the course material. And you should not keep summations, you should develop summations. Hala, we'll do it together now. So let us consider the following example. Let's say an industrial we want to replace a machine A by another machine B. We want to replace machine A by another machine B. Let us see why. So we'll give you characteristics of machine A and machine B, and we want to study if this replacement will be profitable or not. Okay. We have first that I will give you the characteristics of machine A. First, what was the problem with machine A? So for machine A, it's not completely automatic. Machine A is not completely automatic. So we need a worker. We need a worker paid at a rate of $500 per month, and the operation and the maintenance costs are $200 per month. The productivity of this machine, the productivity is 2,000 ports per week. Okay. Where each port can be sold at $5. Okay. Now this machine still have as lifetime 20 years. Okay. The lifetime of this machine, the remaining, if you want, because we are using it already, the remaining lifetime of this machine is 20 years. Okay. And its salvage value 800 or let us say $3,000. Okay. Now, for machine B, we don't need a worker. Okay, so it's automatic. And the maintenance cost are $100 per month. And concerning the productivity, it's 500 parts per week. Also at same rate at $5 per part. Okay. And the lifetime with a lifetime also of 20 years and a salvage value of $5,000. Okay. Now the price of machine B is $100,000. Okay. This is the problem statement. Okay. Now we have several, if you want, questions. Okay. So to start with, we should calculate the ROI. So calculate the ROI of the suggested project or of the suggested change in the industry. How to decide? In order to decide if we should go for it or not, okay, we should first do an economical analysis to see what is the profit, what is the amount of profit, okay, and what is, let's say, the payback period if we want to do the change, to decide if we keep machine A or if we sell it. Okay. Now, to start with, what should we do for the ROI? What is the equation? How do you find the ROI, the rate of return on investment?
Net present value equal to 0 at the end of the year.
Exactly. Net present value at the end of lifetime. Net present value, okay, is equal at n, okay, which is here the end of lifetime is 20 years. Okay, 20 years. Okay, we should calculate now the net present value of this system at the end of lifetime. So our choice will be to replace A by B. If you want to replace A by B, then you can sell A. You can sell it now. Okay, so for the salvage value in general, the salvage value is the value of the system. Here we should give two salvage values. You know why? Why for machine A we should give two salvage values? Who can tell me? In general, the salvage value, we give it at the end of lifetime. Okay? So when after 20 years, let us say, you can sell machine A at $3,000. But if you opt for replacing machine A by machine B, then you should know what is the current price